Hello guys, welcome to Freebird's Crew. So welcome to our next topic of the playlist, data structures and algorithms using Python. So here we'll explain about stacks, that what are stacks, operations, and how to implement them, and what are the some most important questions that are asked in the interviews. So in this whole video, in this whole session of stacks, I will explain one by one each topic. So before starting the video, please like, subscribe and share our YouTube channel. So here is the playlist that has all the data structures and algorithms videos here, and you can just go to my GitHub repository to get the code related to our videos. All my projects and videos codes are here, as we are building on data structures. So the arrays part and stacks part are uploaded here. You can just download that and get yourself practiced. So let's start the video. So the stacks is a basic type of data structure. It's like a thing that we can add data into it and delete data from that when we want. So the main purpose of the stack is that it works on a principle that is called LIFO, that is last in first out. That is, the element that is added in the stack last should be pop out first. As we know that the stack has two principles, the first is push and second is pop. The push means you can add the element to the stack, and the pop means you can get the element from the stack that is recently added. So I can show you the image here. That is, if you want to add element in the stack, you can just add, but the element lastly added, that is 3, should be pop out first. So this is the LIFO principle. And there are two conditions in the stacks. As we know that there is a boundary capacity for every data structure we have. So that boundary capacity is here in the stacks. The first is called overflow, second is called underflow. The overflow means when the stack has only 3 capacity, let's say, and you want to add 4 elements into that. After 3 elements, the stack says it is overflow because there is no space to add the 4th element. And the second condition is underflow, means when the stack is empty and you want to pop out some other element, but the stack is empty, so stack will give you error of the underflow. And here is the topics that I can cover in this whole session. In this video I will tell you about stacks implemented using Python and linked list, and in other videos I will explain you about all these topics. So be with it and watch the whole videos. So stack implementation in Python is here. So stacks has these main functions. The first is to empty, like check that a stack is empty or not. The size, return the size of the stack. Top, returns the top element of the stack. Push, add the specific element that you want to add in the stack. And pop is remove the recently added element from the stack. So in using Python we can implement stacks using 3 techniques. The first is list, the second is collections.dequeue, and the third is queue.lifoqueue. So first is stacks.list. I will explain each topic one by one, so be with it. And stacks using list. As we know that the Python has its inbuilt data structure that is called list, and list has a method that is called append. So we can use append in place of the push operation. And also we know that the list has a function called pop, so there is no need to replace pop with any other function. So we can just use the append and pop functions in stacks using list that works in the LIFO order, and the time complexity of list is O(n). So there is a simple note here that I want to tell you about lists. Though here is that the biggest issue with using list is that as the list size grows, as we want to add more and more element in the stack, so there is need some of the space issue or the speed issues. That is, if the list size is of 1000 or 10,000 and we want to use the append operation, it takes more time, because as soon as the list size is greater, the speed becomes less. So this is the disadvantage of the stacks using list. So how to implement that? We can see here that first we can make a stack, that is, this is stack. We can append into the stack and we can just print the stack, and then we can pop the elements out of the stack. So like see, we can build a stack, we can add elements in the stack, and after that we can pop out element. As you see, the last element should be pop out first, so this should be in the leaf order, so it is correct. The second thing is stacks using collections.dequeue. Collections is a module in the Python, and the dequeue is its class. So using that we can just make a stack using the collections.dequeue class. So dequeue is better than list when we need quick append and pop operations from both ends of the container. As you know that the queue is also a data structures that has the operations from the both of the sides. As you know that the stack has only open from one side, but the queue is open from both sides. So we can use that thing here, and we can just made it a quick append and pop operations from both ends. So dequeue has on time complexity for the append and pop as compared to list. So same methods on dequeue is append and pop. So we can just call the dequeue from the collections module and build our stack, and we can just append the element into it and then pop out element into it, and we can see that it is worked at the same manner as that, but the difference is here. It is the dequeue and the elements are popped out in the LIFO manner, so it is implemented successfully. And the other thing is queue.LIFOQ. Queue is a module and LIFOQ is its class, which is a stack. So data is inserted into queue using the put operation and get using the get operation from the queue. And there are these functions that mentioned here that we can get using this module: max size, empty, full, get no wait, put no wait. That is queue size. That no wait is just a thing that is we have to get the element without any blocking or without any space issues like things. So we can just call the LIFOQ class from the queue and make the stack of max size 3, and then we can just call the queue size of that is using the queue size function, and then add element into it, and then I can just call for the stack is full. If stack is full, it returns true. If not, then it returns false. And then the stack queue size again to check the size of the stack, and then we can just get all the elements and then check for stack is empty or not. So as you know that at first the queue size is 0, and after adding element the queue is full and the size is 3, and after popping all the elements, so here are the elements in the LIFO manner, and the stack empty is true because we pop out all the elements from the stack. So here we can implement stacks using Python using these 3 techniques. The first is list, second is collections.dequeue, third is queue.LIFOQ. So I hope you guys understand that. So now we can just move to the next topic, that is stack implementation using linked list. So let's implement stack with linked list in a way that a stack is then a pointer to the head of the list where pushing and popping operations happen at the head of the list, and a counter is also there that track the size of the stack list. The main advantage of linked list in place of a Python list is that we can dynamically change the size of the stack using linked list. So there is no condition where overflow happens. So here we can make a class node. So and these two are the variables of key and next, and then we can make a class of stack, and here is the top is equal to none because at first the stack is empty. And we can make operation, there is operation is push. For push we can just add element into the node here, and then if node is none, that is if there is if the stack is already full, then it returns heap overflow because there is no node to given to the element, so it is overflow. And if not, then it is start inserting, and at inserting you can just node dot data is equal to x, node dot next is equal to top dot, and node top is equal to node. So this is the thing that is I want to explain you thoroughly, that node dot data is equal to x means we can set the data to the allocated node, and node dot next is equal to self dot top is equal to, we can set the next pointer of the new node to point the current top node, because a stack's pointer is always points to the top node, because whenever we want to perform the pop operation, it should pop out the top element. So there is a pointer that always pointed towards the top. So that's why we can just node dot next is equal to top, and top pointer is equal to node. So here we can just implement the push operation, and after that we can just make operations is that is empty to check if stack is empty or not, and with this peak to get the top element, that is return self dot top of data, and if not, then stack is empty. And the pop operation is like that, if stack is none, like stack is in an underflow condition, there is no element in the stack, so it returns stack underflow. If stack has elements, then it can just give me the stack self dot top is equal to self top dot next. Like we can add a pointer to that, so it can give us that element, as I show here. Node dot next is equal to self dot top, so it is always points toward the top, but the top element should be popped out. And after building such operations, we can just implement the stack like this: stack push 1 2 3, and the top element we can call here. And after that these are the pop operations, and to check the stack is empty or not, we can have this. So as you see, we have insertion of 1 2 and 3, the top element is 3, and removing 3 2 1, the stack is empty. So in this way we can implement stack using linked list. So I hope you guys understand this. If you have any queries, please mention in the comments. I will answer all your questions. So in this video I will tell you about if a given expression is balanced or not. So what is expression? See, if you have this expression, that is it has opening square bracket, opening round bracket, closing round bracket, but not closing square bracket, so that is a unbalanced equation or expression. If it gives like this, so it is a balanced, like it has opening and it has closing. So we can check this thing using Python and using stacks. So we can implement the stacks using collection.deque class with their deque function. So we can make a function here to check expression and pass our expression as an argument into it, and we can check if the length is greater than 1, because if we have expression and we want to check it is balanced or not, it should be greater than the size of 1, because there is two things involved. First is opening, second is closing. So if it is not there, so it is always a non-balanced expression. So we can just build a stack here, and after building a stack we can just traverse our expression one by one. So as we see, we have appending the open braces into the stack, and if we find any closing braces, and if the stack is not, if the mismatch is found, we can return false, and if not, we can just pop out the character from the stack. And if the pop out character is not equal to or not pair with the other brace, so it is also a false condition. We can just make conditions here like that top is equal to ch. If it is not pair, so it is a false condition. If top is this and ch is this, so it is also a false condition. So I can just give like that and return false. And I can just mention the condition like this here. So if this equals, okay. If not, then expression is balanced only if the stack is empty at this point. Like we can just traversing the expressions one by one, and after all the things are traversed, only then the stack should be called balanced or the output is given. So here is thing, return not stack means if we have the expression like if not these things, so we can easily get the true. So as we see that expression is this, it has the opening curly braces, opening round braces, closing round braces, then closing curly braces, opening square braces, opening curly and closing curly, but not the closing square. So it is a unbalanced expression. So if we put it into our function, it also gives us it is a non-balanced expression. So in this way we can just simply implement the stacks and get this function done by using the Python. So our next topic is find the duplicate parenthesis. Like if we have input like this, it has two openings, two closings, so it is good. If it have one opening, one closing, so it is not good. It is not has duplicate parentheses involved. So for this we can easily found that like it is just similar to this, but there are two braces involved. Like we can just first check the expression of length, like it should be greater than 3 because there should be a pair of the braces, like 2 opening and 2 closing. It should be size of 4. So that's why we have to check that the length, and we can make a queue here and for start traversing again. And if current, like see, if current in the expression is not a closing parenthesis, then it should append. Like it is a simple thing that we can do here. It should append all the opening braces into the stack. And after that else, like after appending all the opening, it can just append the closing ones. Like if the top element in the stack is opening braces like this, if stack -1 is equal to opening, it return true, like it has all the conditions matched. And if the pop till opening is found for the closing, while stack is not equal to opening, it should start popping every time. And if this condition occurs, then for this it should happen start pop. And if we reach here, then the expression does not have any duplicate parentheses, because if it reached here, so like I can tell you that if it's found out its pair, so it is just stop at here. It should not go to here, because this condition is only for this expression that we have maintained here. So after we can give on this expression, it will give us the output like this. It has 2 opening and 2 closing. It will give us the output. So these are the simple things that we can implement using Python and using stacks, and you can check out our expressions is balanced or not, or it has duplicate parentheses or not. So this is all from my side for this video. I hope you guys understand this, and if any queries happen, you can just comment down your queries and I will answer it very smoothly. So in this video I will tell you about another example on stacks to decode or encode a string or a thing to a minimum number. So our problem here is that we can have to decode the given sequence into a minimum number without repeating digits. Like in this, I use these two alphabets I and D, where I denotes that it is the increasing sequence and D denotes that it is a decreasing sequence. So with the help of that, we can have to decode it into a minimum number. Like if I say that this sequence is equal to this number and this is equal to this number, so I can explain about each step in this video. Let's start the video. So we have to first create a function decode, and that we have to create a stack and result function variable, a string, and for each variable we have to traverse in this string. We have to push that index plus 1 into the stack. Like we have the I and its index is equal to 0, we have to push in the stack is 0 plus 1, that is 1, and in this way we can push all the elements into the stack and pop out from that in a way that it can become a minimum number. So for this for loop, we can have that thing that we can just append by adding plus 1 into it, and then we have this condition that if it is equal to the length, it is not equal to length, because if it is not equal to length, then it is a number that is not exist in our stack, and all the sequence is equal to I, because we have to find only a sequence that is equal to the length or is equal to the I, because I is an increasing sequence, and whenever it finds I in the stack, it just popped out the values from the stack in the LIFO manner. So here we can just, whenever we find I, it can just push out all the values. So whenever this condition is true, it can pop out all the values from the stack here and print the values and give us the result. And I can use these two print statements to show you how it exactly works. That see, first we have the D. So D is stored in it as 1, and then I stored it as 2, and when it's I found, it can just pop out all the values like 2 and then 1, so it is 2 1, and then we have again I, so I is 3 and it is again equal to I, then it is pop out, that is 2 1 3. Then again is D, so D should be not pop out because this condition will be false for D, and then we can have I, then it is 4 and 5, and it can pop out in a way that 5 4. So in this way this thing work and can generate a minimum number from that. So I hope you guys understand all the concept of this decoding and encoding thing with the help of stacks, and you can create more things from this. You can apply it in the encryption and decryption cases, and you can make more things out of the stacks. Thank you so much. Hello guys, welcome to the next video of data structures and algorithms playlist. Topic is stacks, and we have another example or another topic in stacks, that is in order, pre-order, post order, or the level order traversals of tree. And as we know that we have a binary trees and we have to traverse in a different ways using breadth first and depth first search. So in this video I will tell you all about that, and so be with it and watch whole video to know more about it. So let's start the video. As we know that a tree is traversed in multiple ways, like we can use depth first search in that, that is includes pre-order, post order, in order, and also the breadth first search that includes the level order traversal. So a tree is a non-linear data structure, that is there if we have a given node, then there can be a 1 or 2 ways to go to the next node. So for do that, we can just do the in order reversal in a way that just starting from the root node is that we have to first recursively traverse the left subtree and then come to the n, that is root node, and then print the n, that is root node, and then again traverse the right subtree. In this way you can just traverse the tree using the in order traversals, and we can do it by using the depth first search. Like we have this diagram here, like first we have to traverse the left subtree. The left subtree, we can go into the depth of left subtree is 4, so there is 4, 2 and 1, and now we can go to the right, and right is go to the depth of this thing, and that is 7. We can go to the 7, 5, and then again depth, then 8. Then we can again go to the root node, that is 3 and then 6. In this way you can just traverse the whole tree with this and can get the values from that. So I have the two implementations of it, that is first is recursive implementation and second is iterative implementation. So first we can learn about the recursive implementation. So the recursive implementation is just a simple thing that we can have just a class here that is contain the data node, left node and right nodes of all the trees, and now we can create a function that is in order recursive function. If the tree has any node, it returns false. So just like we can write it here, it returns false here, and if not, then it can just traverse first left subtree, then print the root node and then go to the right subtree. So in this way, this is how things works in the in order traversals. And now we can create a object from the node class and make a tree here and can call the in order recursive function and can print out the values like this. I hope you guys understand this recursive method, and now we can move ahead to the iterative implementation. So in iterative implementation, there is nothing different, but we have to just build a stack from the queue class. That is, we have the queue, there is queue from the collections, and we can make a stack from it, and we can just root node is equal to the current node, that is the top node of the tree. And now we can just run a while loop on the stack, and if the current node is not none, it can just push the stack values and move to the left child. Like it can just start traversing from the left. That is, as you see that it can just start traversing from the left, and if left is completed, then it can go to the our root node, and then it can go to the our right. So in this way it will work. That is, first it will go to the right subtree, then root node, then left subtree, root node, and then right subtree. And in this way it will work in this manner. So in this manner you can just do the in order traversal. So our next thing is pre-order traversal. So pre-order traversal is just like the in-order traversal, but the way to traverse the tree is little bit different. That we have to first print the root node here, and then we can recursively traverse the left subtree and then right subtree and come back to the root node. So this all can be done using the depth of search. So as you see, we have to first print the root node. So we have to first print the 1 and then 2 and then 4, and then again we go to the root node of right subtree, that is 3, 5, 7 and then 8 and then 6. So in this way you can traverse the tree using the pre-order traversal. So here we can the recursive implementation of that, where we can just simply do the things like we can do in a in-order traversal, but the main difference is that we can just have the things right here as per our conditions. Our conditions are, first we have to print the root node and then the left and then the right. So it can work in that way, and we can just make an object of the node class and make a tree, and then we can call our function and can get the values. And the same thing happens with iterative implementation, and there is a little bit difference in that we have to first append the root node in the stack here, because the root node should be printed first. So we can just print it first in here, and then it can goes to the things like that. It can go to the right and left. It can and then it can goes to the left, and then it can go to the right and pop out all the values from the stack. Like if current node is not none, then it can print out the root node, and then it can go to the right, else it can go to the left. Because if we have this tree and we can go to the things like we have reach here, it can go to the right, and then again it go to the left, again it go to the right and go to the left. So in this way it can just start traversing in a manner and pop out all the values for us. So again we can make an object from the node class and make a tree and do the function. And our next tree traversing method is pre-order traversal. I am sorry, there is a little bit difference, is that this is our post order. Okay, this is our post order traversal. That's okay. So now we have post order traversal method here, that it is no very much different from that. We have just call it like that. We have just first the left subtree, then right, and then the root node. In this way it can works like you can see that first the left, then right, and then the root node. So first it goes to the left, that is it is the 4, then 4 2, then it again goes to the right, and then it again goes to the right, and then it come to the left and right and left. So in this way it can just traverse the whole tree. Like we have the recursive implementation here, then it is also same as that. The difference is that we have the post order method call for the left subtree first, and then right, and then the root node. And again we can make an object of the node class and make a tree and apply the post order recursive method on the tree. And similarly for the iterative method, the thing is just as the same. We have just append the root node first, and then make another stack out of it to save all the values of the stack into it to get the most out of the stack. And there is no discrepancy or space issues in that. So due to that I can make another stack here, that we can run a while loop on the stack, and if the current is root node, it can go pop out the values and get append into the out. And then if it is left, then it can append it to the stack, and it can right append it to the stack, and then pop out all the values from the stack. In this way this all things works as here, and we can get to the post order traversals iterative methods. I hope you guys understand all the concepts from here, that how can we traverse a tree using the in order, pre-order, and post order traversals. So our next thing is the level order traversal using the breadth first search. As you know that we have the levels here, that is 1 2 3. So these are the levels. So this level order traversals works like that. It can go to a particular level and then print all the values on that level. If I say that I can go to the level 2, then it can print the values 2 3 from here. So we can just make a simple recursive function for that. Like here is our here is our node class, and which has the key left and right values. And now we can create a function of the print nodes, that if root is none, then it is return false, and if the level is only just 1, it can print the root key, and then it can just recursively printing the left subtree values and right subtree values on a particular level. Like if I come to here, it can just print all the values on that level. So our next function is the level order, that it can tells that which level have to be traversed. Like the first level is 1, and it can just increment the level 1 by 1 up to a tree which have. Like it can just call this function print order print nodes recursively here. So I can just have the thing like that. I can make a root node 15. 15 should be called first, and then 1 or 2, because this is level 2, and this level 3 and the level 4, it can happens like that. I hope you guys understand these things very clearly, and these are from my side in the stacks. I hope you guys like it, and if you have any queries or any things to ask, you can ask me in the comment section. I can answer you as soon as possible. And